Hi, everybody. Today's lecture is going to focus on section 1.7, which is about transformations of functions. So we're going to start off with a relatively simple example. We've got a function. Now, this particular function, I'm showing you the one that's in the book we're going to work with. It doesn't have a formula for it, okay? But it is a relation, and it does pass the vertical line test. So you see that is, in fact, a function. What it is, there's 4 points in the plane: 0, 1, 2, 3, 4, 3, and 5, 5. And the function is defined rather, just as connect those guys together with straight lines. The points that are along these straight lines, and including the points, the given points, that constitutes the function. We don't have a formula for it. But we do have a way of computing a value. You give me any number between 0 and 5, and I come up and measure how high the graph of this thing is, and that gets me the value of the function. So we're going to first look at adding something to the function. See here, right here, we're creating a new function, g of x. G of x is that, but it's equal to, just get the value of f of x and add 2 to it. Down a little lower here, they create a little table. Got a bunch of different x values forming the left-hand column. The points that were given, well, okay, wait, are these x values? Yeah, they're the x values of the actual points here, 0, 2, 4, and 5. And so x and f of x, those are the x and the y values. So then f of x is just the second numbers in each of those, 1, 3, 3, 5, 1, 3, 3, 5. Great. How do you get g of x? Add 2. So the numbers are 1 becomes 3, 3 becomes 5, 3 becomes 5 again, and then 5 turns into 7. So the pairs in this new function, g of x, are 0, 3, 2, 5, 5, 5, 7. What does that physically look like? Well, I bet you that's clear to everybody. It just moves everybody up 2 units. Let me show you this in a Desmos graph. I already pre-loaded this graph with stuff, but I didn't make it visible. So I'll just click on things and I'll show you. The point 0, 1, 2, 3, 4, 3, and 5, 5. And you really don't want to know the Desmos syntax, at least not right now. But this is the thing that draws the junk that connects between those guys. Okay. So I've just turned it on. Now, you may see I have a slider here. The slider is set at 0 right now. That's because there's another graph that, again, has that horrible syntax, but is just what we said g of x was. It's add 2 to all the values of f of x. And so you see the g of x, when I turned it on, is right on top of where the red graph was. We were going to add 2, so let me set the slider to 2. That's what g of x looks like. And I hope you see this is what's known as a rigid motion. It's like it grabbed hold of the red thing and shoved it up in the air without keeping everything, in the same relationship to one another. But everybody's moving together up 2 units. All right, so that is a type of transformation we call a vertical shift. When k is 2, we've got that shift by 2. If I make k be 1, we're only going up 1 unit. I can move the slider up as high as 5, and then it would have gone off the screen, so I set it down there. And I can also have negative values for the shift. I can make the g of x graph go down below the x, below where the red one is. Again, I limited it to -5 because, well, I didn't want to go off the screen. But really, this k could be any value, including, I've made it nice integer values. It could be things like 0.22 or something. You can shift any amount. So this is kind of cool. We've got a way. Think about this. We've created a method for, in general, if you've got some function, how you can shift it up and down vertically. So let's record that. Given some function f of x, and I guess I'll think about the graph of that function. We can get a shifted version. We can create a vertically shifted version of it. Merely by adding on the outside. It's important that it's sort of f of x plus something after. I could name it g of x if you like, but I think it might be nice to just write it as y equals f of x plus k. And this is going to move k units vertically. If k is a negative number, it'll move down. If k is a positive number, it'll move up. Cool. Well, you know what? I feel like I should do an example that's not quite as made up as this one, this weird little thing that's drawn between a bunch of points. Let me get a new one. I'll save this as it stands, but we'll create a new blank graph. Here's a function you guys should know pretty well, the square root of x. There's the graph of it, square root of x. But if instead of just the square root of x, I throw in a plus k, and it'll add a slider for k. Now this slider, I think by default, it goes minus 10 to 10, and it starts out with k equals 1. There's the original graph, and if I change to any value of k, I can get a shifted version of it. In fact, this has the nice feature that you can animate and make it go up and down really fast. Here. Go. Right? Any amount of shift you want. You can slide that baby up in the air. You can push it down below the x-axis. Just add a plus k on the outside. I feel like that's kind of fun to do, but I better stop. Let's get back to this graph because we're going to need it in a minute. Right, so let me pull back to the textbook and let's think about what this changing, they're just showing you two separate graphs. I think showing it on Desmos was more useful there. And this is the summary of it. This is how you do a vertical shift. They separated it into two cases where you do plus k to shift it up units and then minus k to shift it down units. I feel like that's a little weird. You should just say k could be positive or negative. And if k is negative, that's like subtracting some number. But it's a matter of perspective, not a big deal. This business of adding k after the function is computed is kind of cool, and it lets you, you may think, well, what if I did the adding somewhere else? That is, well, see it right here, let me highlight it, where we've looked at g of x is f of x plus 2. If you say it in words, it sounds just like what it did before, but if you pronounce the parentheses, f of x plus 2 versus f of x plus 2, then you'll get it. So this is making an addition to the function before, that is, I said it wrong. That is making an addition to the variable, the input variable, before you feed it into the function. Now, if we were going to do that with the given function, the one, for instance, like in the Desmos window, this red one, actually let's turn off the green one for now. That will cause us a little bit of a problem. Here's the issue. Suppose I wanted to calculate the new guy at 5. X would be 5, great. Now the formula there said add 2 to it, so x is 7. And what y coordinate goes with that? There isn't one. In fact, if I want the input to f to be 5, I actually have to make x be 3. Think that through for a second. If I had x equal to 3, when I add 2 to it, I get 5, and then I'll get this y coordinate. Yeah? And so the domain of this function, you can just visually see it. You've got x coordinates that go from 0 up to 5. What would be the range of values for the x if we were doing g of x, where it's f of x plus 2, f of x plus 2, it actually goes from -2 to 3. Now, I think I made a version of that. Woohoo, I did. So it should start with a shift of 0. I won't subject you to the Desmos syntax for this yet, but the purple graph rather is the same thing as the red graph, but with what's known as an inside change. I'm going to point that stuff out to you. That plus k out there, that's known as an outside change. Outside referring to outside the parentheses. You can make an inside change, which means inside the parentheses, and well, we're going to see in a second what that does, but maybe you can guess by parallelism with the paragraph I had above. Given y equals f of x, we can create I'm going to leave a blank for it, shifted version. That is not the letter S. I don't know what happened to my brain right there. I had a brain failure. Version. And it looks like this. It's y equals f of x plus k. All right. Well, what's supposed to go in the blank there? Before it was vertically shifted. Maybe it's obvious. This is horizontally shifted. I want to show it to you now. If I change the value of the slider here, it moves it. And you notice that I've right now, well, let's do 2, because that's the shift amount they asked about in the book. I did a plus L in there. You can just see the corner of it in the Desmos screen, X plus L. And when I set L to 2, we created a shifted graph, 2 units, horizontally. But to my mind, at least, it seems like it's gone the wrong direction. You see, before when I added 2, I went up. I went in the positive y direction. Here, when I'm adding 2, I'm moving left, which is in the negative direction. The kind of change we made here is an inside change. It's inside the parentheses. And the easiest way to deal with this question is just get used to it. Inside changes work backwards. They go the opposite direction you expect. If you just accept that with me, then this will stop seeming weird. You can think your way through this. If I am trying to get x plus k to be in the range from 0 to 5, like for this graph, well, then I've got to reduce the x values by k units so that when I add k, I come back into the desired range. But reducing by k units means moving to the left. So maybe that explains why the inside change kind of goes the opposite direction you might expect. Okay, so let's next do something kind of cool, which is to put these two things together. Okay. I don't think I'll continue working with this piecewise defined function. So again, let me pop a new worksheet up. Blank graph. Here's a nice graph to work with. Y equals x to the second power. It's a familiar graph, a parabola. What we can do is combine having inside changes and outside changes to allow us to draw a parabola pretty much anywhere you want. So the inside change is to add something to x before you do the squaring. That is, inside the parentheses. Probably got an equal sign in there. That was supposed to be a plus sign. X plus square k, then square. The outside change would be then to add something. And I'm going to create two different sliders here. They both start out at 0. They should both start out at 0. They both started out at 1. Anyway, if k and l are both 0, we get our ordinary parabola. That's fairly obvious. If k is increased, my parabola moves to the left. But if L is increased, remember L is the outside change, my parabola moves up. So we can probably move this guy all over the map by starting that one and then starting this one. And no need, it moves along. The idea here is that we can create a parabola there's this one point at the bottom of the parabola which is moving, so it's hard to point at. That lowest spot on the parabola is known as the vertex of the parabola, and that sort of locates it. So I can arrange to put that vertex wherever I like. Suppose, as an example, I wanted to get to this point. That's -3, 2. Okay, that's a point. Well, I am just going to need to make k be +3 and L +2. There it is. And I put the vertex right at the point I desired. If I wanted to make that point be +3, 2, well, how do I change things? There, I need to make k be -3. If I want to move to the right, I use a negative value on the inside change. If I want to move to the left, I use a positive value on the inside change, and vice versa for the outside changes. Well, now, what we've done, both inside and outside changes so far, has been adding something, a shift. That's what adding something does. It shifts you either vertically or horizontally. What about if we multiply? It's a reasonable next question to ask. So what does that do? In other words, shall we do an outside multiplication first? Let's think about what happens if we have y equals, I guess I'm going to use k again, k times f of x, as opposed to k plus f of x, or f of x plus k. I don't know, where you do is it times k or k times? That's the same thing, yeah. So, let's get rid of this guy. I'm going to keep k around because we need it. I don't need that point. What function should we look at? How about f of x is x cubed? Or I'll type it as y equals x to the third power. That's a cool looking graph. It's sort of like a parabola, but it's like split in half. There's a upward curving parabola on the right and a downward curving parabola on the left. All right, let's throw a k times in there. What the heck? Oh, k was -3. Wow, that's sort of bad for me to start k off at a weird number. K should be 1 to begin with, because then multiplying by 1 doesn't change anything. What does multiplying by larger numbers do to the graph? Well, I don't know visually if that does what you think it does, or what it looks like it's doing. In my mind, I'm thinking about as I multiply by things, I'm seeing the graph shrink inward. That's not really what's going on. The graph's points are actually moving upward, aren't they? Because what we're doing is scaling the y-coordinate by some big number. So we're not actually going squishing, we're stretching when we do that multiplication on the outside. In fact, that's what people most often call it. Y equals k times f of x is a vertically scaled version, or vertically stretched, some people might say. I like the word scaled myself, because if the number is smaller than 1, it will get not stretched but compressed. So scaled kind of incorporates both of those ideas. A particularly interesting value happens if k is negative, but let's make it be -1. wait a minute. Maybe we shouldn't do this with the slider. Sorry. Let me put the slider back to a value of 1, and we'll just make a new graph. Y equals negative 1 times x to the third. Physically, how is the red graph related to the black graph? We have an outside change, so we're changing things vertically. And what I did was multiply y coordinates by -1. That turns them upside down. If y was positive, like in here, the modified one on the red graph becomes a negative number way down here. If y was negative, like here, then when I multiply a negative number times -1, it becomes positive. There. So what's going on here is the graph has physically turned upside down. This isn't the best example to use to see this. Let me give you another graph that we probably have run into before, the absolute value graph. Absolute value of x. And then let's look at what -1 times the absolute value of x is, or just oh, we can do that. Yeah. Well, it looks like I've made a giant X, but the top V of this thing is the black graph, and the upside down version of it flipped across the x-axis. That's the red graph. So vertical scaling, when the scale factor is -1, is what's known as a reflection. It's a special case of the general scaling question. Like, I guess I can take that out of there and just show you. If I make this be a negative number, the absolute value graph becomes inverted, reflected across the x-axis. But it's kind of neat, I think, to see it in the full sweep. When I have large values of k, it becomes really stretched tall. When I get values, well, when I get 1 in there, I get sort of no effect, but then values less than 1, it gets flattened out or compressed vertically, right? And then when I get negative values, it's upside down and either compressed or stretched, depending on how big the absolute value of k is. Is that going to be any fun to watch in an animation? Big values of k, small negative values of k. It's kind of fun to see. I'm going to stop. Okay. What about if we made inside changes multiplying by something? Now, there's a little piece of algebra that I want to show you. If I had the same function, x cubed, and I put a minus sign out front of it, so this is one kind of change, take -1 times x cubed. Or I put a minus sign inside, or this was an outside change multiplying by -1. Here's an inside change multiplying by -1. It turns out these are the same. Yeah. So in this case, for x cubed, a vertical stretching and turning upside down by a factor of -1 looks just like a horizontal change. That's what happens with inside changes. They make things happen horizontally. So I want to show you a graph that where this feature doesn't happen. Okay, let's try this guy. Let's start off with x to the third minus x. Now that graph, I'll zoom in on it a little bit. That graph has some features that will let me know whether it's been changed vertically or horizontally. You see where the features I'm referring to are the points where this thing hits the x-axis. They happen at -1, 0, and 1. If I squish it sideways, that's making a horizontal scaling. Those guys are going to move, or at least the outer ones are going to move. Whereas if I scale it vertically, they're going to stay in place. So let's see that with an outside change, k times x cubed minus x. K right now is, no, it's not turned on. Wow, k is huge right now. Let's make k be 1. There it is. Looks just like the black graph. But if I move k up to a slightly larger number, notice how the zeros stay put, but what used to be this little hump here has become a much taller hump. It's like and there's a dip over on the right-hand side that was down to about a value of maybe almost -1. Now it's around -2. Well, it's closer to -3, I guess. Well, yeah, this is less than -1. Or, wow, said it backwards. It's smaller in absolute value than -1 is. Anyway, that can we get a number on it? -0.4, more or less, and then this one is -1. Yeah. Anyway, they've been scaled by this factor, 2.8. You could verify that with a calculator. It's the taller I make it, the more stretched out it gets. But that's just quantitative. I can also make the k value less than 1, and that'll create something that's kind of flattened. In fact, I can flatten it. Well, if I just hit 0, I can't seem to make it go to 0. I can make it turn into a horizontal line with height 0 if I multiply by 0, which maybe that's not very surprising. But if we go into negative territory, that's what's kind of cool. It turns it upside down. In fact, when k is -1, you see how we've got a reflection in the x-axis here? That's definitely not the same as a reflection in the y-axis for this graph. Or is it? Darn, it really is. What's going on when I know that we were thinking about this as an outside change, so I was affecting the y coordinate, making the y coordinates of points go to their negatives. I'm making a vertical shift. But this function, I shouldn't have said shift, a vertical scaling, it looks like it's a horizontal scaling. Let's actually do a horizontal scaling on this, and I think we'll then see why. I can just change this red graph so that it doesn't look like that. Let's do k times x cubed and in this case, everywhere where we see an x, we've got to replace it with a k times x, or x times k, it doesn't matter. All right. Right now, k is -1. And wow, this does indeed look like the same graph. But if I move k to non-trivial values, for instance, when k is 1, it looks like the original graph. If k is bigger than 1, it's as if the graph has been squished in sideways. So we have affected a horizontal scaling. If I make k really large, it crushes it a lot. Now, do you see how this is just backwards from the way a vertical scaling worked? Again, the inside changes kind of work in the reverse of the way we might intuitively think they do. K is 10 practically turns it into a flat thing. And negative values of k are just going to, well, I want to get -1. Let's see if I can adjust it to that. There you go. Oh, I moved it. Boy, it's really hard to get that to adjust right on -1. Turns out, for that one special value, -1 looks as if it could have been a vertical change as well as a horizontal. But when you see k larger than -1, that's clearly some kind of a change that happened horizontally. Now, the reason that we're seeing a vertical reflection and a horizontal reflection ending up giving us the same value or the same graph is about the nature of this particular function I chose. Do you notice how 3, the exponent on x cubed, is odd, and the other exponent, which isn't really there but you can imagine it there as 1. That's also odd. This guy is made up of odd powers of x. That makes it an odd function. And odd functions have exactly this property we've been talking about, that a vertical reflection and a horizontal reflection, that is a reflection across the x-axis and a reflection across the y-axis, give the same result. You can even say, do the 2 reflections, and you'll end up back where you started, which is fun to play with. Okay, so we've thought about inside multiplying, outside multiplying, inside adding, and outside adding. Let's put all that together. Let me just turn these babies off. We don't need them. I'm going to create a function that's going to have 4 different constants associated with it. What should we use for the graph that we'll play with? I'm going to do the square root. So we'll start with y equals the square root of x. Okay. Now, let's make a modified version of it where we will both multiply and add on the inside. So square root of, let's say, ax plus b. And then we also want to do outside changes. So that'll be times c on the outside and plus d on the outside. You see how the function is square root. Inside, before you get to the square rooting, we have this changing by multiplying and adding something. And after the square rooting, we've got to multiply by c and then add d. So we got sliders for all that stuff. What values of the slider variables should I have had to make this thing come out looking like the original graph? The multipliers, a and c, should have been 1. They're okay. They are 1 by default, but the adds should have been 0. Whoop. Can't seem to make it happen. 0, and there we go, right on top of it. Now we can play with all 4 of these numbers, and you can visually watch the effects of them. Just got to remember what they do. B and D, those are the ones that take us up and down. So here's B. Wait, B is moving us side to side. What did I do wrong? Oh yeah, because I looked in the wrong place. B is an addition on the inside. That's a horizontal shift. D is an addition on the outside. That's a vertical shift. Notice again, the vertical shift, when I go to positive values of the number, I go up. The horizontal shift, when I go to positive values, it goes to the left, backwards. If I move these other guys, A is going to scale me vertically. A is, what did I just say? I said it wrong, didn't I? Because what did A do? A scaled us horizontally. And C scales us vertically. It's even possible to do a combination of those. What have I got here? A is 3.3 and C is 0.7, and it just looks like I didn't do anything to it, doesn't it? Looks like it's more or less parallel with the original graph. What's going on? Well, it happens that when you have a power function, there's an interplay there's a trade-off between inside changes and outside changes. Let me give you a quick example of that on the paper. Suppose I had square root of 9x. That's looking like an inside change. By scaling things by a factor of 9, that would cause things to compress horizontally by a factor of 9. But, you can, if you have a power over a product, that distributes. So this is equal to square root of 9 times square root of x, which is just 3 times square root of x. And now what was an inside change, which would have caused horizontal scaling, is now turned by algebra into an outside change, which causes vertical scaling. That is, for a power function, and x square root of x is a power function, and an inside change of some amount can be found to be equal to an outside change of some amount. Man, I'm having a little bit of dyslexia here between insides and outsides. I think I better do an example of that with something that's not a square root, because that might make you think it's not a power. Of course, it is, because square root of x is the same thing as x raised to the 1/2 power. All right, but let's do it with something that's more obviously a power. How about if we had x cubed? Well, I could do an inside change of x cubed. Take 8x. Sorry, get a little carried away with that. Maybe 2x cubed. And what would that do? Multiplying by 2 on the inside should horizontally scale things, shrinking by a factor of 2. So it would be half as wide as it was. I guess I better prove that to you. Here's x to the third. Looks like that. Here's 2 times x to the third. The new guy is the green one. You see how it looks like it got pushed in from where the blue one was? And if I make that be a, I can then change how much it got squished. Including I can squish it right through the axis and have it turn out the other way. Have the x coordinates turn into negatives of what they were. But moving this a is actually changing x coordinates, because it's happening on the inside. I'm multiplying the x coordinate by something. On the other hand, let me just throw in a new one here. Get rid of that one. What if I multiplied on the outside by something? Let me use perhaps slider C for that. What if I did C times x to the third? Okay, that's weird. What value did I start with? I said I was talking about over here on the piece of paper, x being turned into 2x. So let's set a to 2. There it is. What value of c will create that same graph? Because I can arrange for it to happen. Now I'm stretching vertically until those two guys line up, and wow, it seems to be 8. Does that make sense to you, that this inside change, x cubed being turned into 2x, quantity cubed, is the same thing as an outside change with 8 times x cubed? Actually, yeah, it does, doesn't it? If you distributed this cubing across the product that's right there, you'd get 2 cubed times x cubed. 2 cubed is 8. Cool. Well, that's where we need to be for today's class. I wanted you to see what happens when you combine all 4 types of transformations together. That'll do it for today. I've erred in the opposite direction. Now, the first video I made for you went longer than 50 minutes, and this one is only about 40 minutes. So maybe that evens things out. I'll try for a solid 50 next time. See you later.